Okay. We talked Monday about the whole picture of the matter being divided into pure substance and elements. And we talked that the element itself is made of atoms. Those atoms are made of electrons, protons, and neutrons. Furthermore, we talked about the pure substance is just a mixture of pure substance is a mixture of atoms together with the fixed composition. That's very important. Like when I say I have a pure substance called H2O, correct? H2O, you learn later on, H2O is not tap water or something. The name of it is chemically is dihydrogen monoxide, dihydrogen monoxide. So if I have a pure substance called H2O, dihydrogen monoxide, and I look at this is a pure substance. So what's the definition of the pure substance? It's a combination of elements with a fixed composition. So this is two hydrogen atoms in one, with one combined with one oxygen atom. Now, if I find H2O here on this Earth, or in Mars, or anywhere else, the combination is still holding, and it's two hydrogens atoms to one hydrogen oxygen. That's what we mean a pure substance. Now we can mix pure substances together, and we can obtain two types of mixtures, homogeneous or heterogeneous mixture. And we said in case of homogeneous mixture, if as you recall, that homogeneous mixture is the distribution of the pure substances within the mixture itself is uniform. You will see just one single layer. You will see what? One single layer, not see two layers. So if I mix sugar and H2O and stir the whole solution, I make a solution that's a colorless solution, and this solution has one layer, correct? So there's not two layers or three layers, something. So the sugar is totally dissolved in H2O. However, I can make heterogeneous mixture by mixing H2O and oil. Oil is less dense, we say. Anything less dense will float. Anything heavier will sink. So H2O will sink, and the oil will float. So I will see two layers. One layer is for the oil, the second layer for the H2O. So what is the definition of heterogeneous mixture? Is a mixture by which is the distribution of the pure substances. Oil is a pure substance, H2O is a pure substance. When I mix them together, they get into disturbance because of the difference in their solubilities and densities. They will make a heterogeneous mixture, so the distribution of those pure substances within the mixture is not uniform, is not by all means uniform. So therefore, you will see two layers for each pure substance. So each pure substance will come with its own layer by itself. And then we talked about homogeneous mixture and heterogeneous mixtures. Those we can separate them into their original pure substances. If I have an oil and I have H2O, I can separate them. And there are many methods or tools for separating those heterogeneous or homogeneous mixture, correct? Heterogeneous mixture is very easy to separate because there are two layers. They're already separated in the sense. So it's very easy to separate. I can use too many techniques or methods here for separation. I can use decant the oil, correct? Or just suck the oil with the pipette and keeping the H2O at the bottom. I can decant, or I just can distillation. The H2O will boil around 100 degrees Celsius. The assumption we are at 1 atmospheric pressure. We are close to the savanna. Savanna is at sea level. So when you are at sea level, you speak about 1 atmospheric pressure, 1 atm atmospheric pressure. So the H2O will boil what? Will boil around 100 centigrade Celsius. Now, if you are in the mountains, that's totally different. If you are in Colorado, Denver, like 1 mile high of the sea level, 1 mile high from the sea level, so the H2O will boil 75 centigrade Celsius. will boil early at lower temperature, correct? Not 100 degrees Celsius. So whenever we are talking about boiling points, we refer boiling points to 1 atmospheric pressure, and exactly at the sea level, like Savannah. Savannah, it's at sea level as a city, while Denver is 1 mile high above the sea level. So you can see the difference. Savannah, the H2O will boil at 100 centigrade Celsius. Denver, the H2O will boil at 75 degrees. I mean, the mountains, up in the mountains, correct? So what else we can look at the, we can look, if you look, we can have distillation, decanting, we can have crystallization, we can have filtration. All those physical methods, the advantage of these physical methods, they don't alter, they don't change the composition. So if I distill H2O out of oil, by the way, oils are boiling at higher temperature. You can see, you can cook with the oil, correct? You can cook with the oil because the kitchen heat or furnace, the kitchen when you cook, or the stove you are using, can go maximum maybe 400 centigrade Celsius, 350, 400 centigrade Celsius when you push it. So around that temperature. That temperature is enough to let you cook most of the food, correct? But you cannot do much of work if you need higher temperature for something else. So, but anyway, so the we can use filtration, we can use crystallization, we can use decanting, we can use gravimetry. So there are too many physical methods and procedures. You can separate those mixtures out of each other. So, but the good thing is you don't destroy the what? The composition. So you are not destroying the composition. Now, if you use too much for example, gravimetry, too much of heat, as we talked last Monday, you might alter the compound itself. The pure substance will be no longer pure substance, might be changed. Like if you cook the eggs too much, you are destroying the peptides, the amino acid chain. So you have about maybe 20, 30 amino acids together linked with the peptide link. And then if you heat too much, one of them maybe or two of those chain links will be getting out of the chain itself, and therefore you lose the nutrition benefits of that proteins inside the egg. Are you following me here? So it is very important that use tools or physical methods that will not alter the composition. If you start altering the composition, you are producing a new compound. This is no longer pure substance. It's maybe mixture. Whether it's homogeneous or heterogeneous, you have to look into it itself. We have distillation, and in the lab, if you look at the distillation here, let me get to the pen here. So here you put your mixture here inside this. Let me get the pen is working here. Okay, I'm trying to get the pen is working. Okay, so here's your mixture is inside this flask, correct? Two components, for example. Mostly distillation is two components. And we separate the distillation of mixture by the boiling point, because we are boiling the solution, so we are taking those by boiling point. So the first one will go first here. Out of this, let me change the color here. We'll go out of this and we'll start condensing to this inside. Start condensing. That's the one with the least boiling point. The least boiling point will go first, correct? So if I have isopropyl alcohol, rubbing alcohol, antiseptic used to kill bacteria, you go to Walmart or Target or any groceries or any pharmacies, they have it. So 2-propanol or rubbing alcohol, the commercial name of it, you can use it. And this mixture, 70%, 30%, but you want to get 100% rubbing alcohol. That's we can use distillation. So rubbing alcohol boils at 78, 75, 78 degrees, H2O at 100 degrees. That's with at 1 atmospheric pressure. So first here will come the least boiling point, the pure substance that has the least, which is the isopropanol or 2-propanol or rubbing alcohol will come first, and will be gathered in this flask. So this flask is the first one. H2O will remain. The H2O will remain inside. Let me change the color here. The H2O will remain here. So you are separating mixture of two, rubbing alcohol and H2O, correct? And separating, this is the least one, which is rubbing alcohol will come here in the flask there. That's the least one here, least one. And here will be, it has the highest boiling point, will remain at the beginning flask, the boiling flask. This one here is the receiving, this one receiving here, and this one is boiling, correct? The same thing with you heard about the 100% ethanol. How you get 100% ethanol? You have to go through distillation. You distill this one here. Ethanol will get first to the other side. H2O will remain the other side. So you produce 100% ethanol, which is by all means not drinkable. It's very dangerous for the liver and the kidneys. And some people, I don't know, they're hooked or addicted to the type of vodka. Did you hear about vodka? That's a Russian drink, which is almost 100% ethanol, which is not good for the kidneys, not good for the liver. It destroys the livers. So, but anyway, so this, if I have a mixture, I want to make 100% alcohol, correct? So then I take this distillation apparatus here, boil the H2O, the ethanol come first in the receiving flask, and H2O remain in the other flask, in the boiling flask. So this is type of how you separate mixture. So you can separate this one here by different in the solubility, correct? Let me go here and take the emission out. If I go here, for example, I can separate mixtures with the help of their, with the knowledge about their solubility, correct? Of their what? Solubility. So if I have, for example, I have two mixtures. Okay, I have sand and what? I have sand and salt. I think this will be in the lab experiment, I think. So I have sand and salt and sodium and kitchen salt, sodium chloride. So, well, I'll take the opportunity to look into the solvent that will dissolve one and will not dissolve the other one. And that solvent has to be cheap, available, and non-toxic. So I'll use H2O. When I add a mixture, heterogeneous mixture of salt and sand, the H2O will come and dissolve for me what? The kitchen salt, the sand will remain there. So I can decant the solution of H2O and salt, and the sand will remain in the what? The sand will remain in the other flask or other container or beaker, correct? So the crystallization is you take the solubility. So what's happened is you take the material, and crystallization is not per se used for separation. It's used for making the compound more pure, purification of the compounds. We don't use it to really separate things, but we have, for example, if you have seen before, you will produce, for example, that's organic. If you go for organic, you will produce aspirin, correct? Now the synthesis of aspirin in the lab will yield salicylic acid, which is the reactant with acetic acid anhydride. Now the problem with, you don't need salicylic acid. the aspirin will be too acidic. Can't even take it as an aspirin. So what you will do here, you will go through crystallization. You look at the, let me just, you will go through crystallization in the sense you want to get the salicylic acid out of your way and keep aspirin inside. So you look at the solvent that really dissolves salicylic acid, but not aspirin. Are you following me here? So H2O will work. Salicylic acid will be more soluble than, or ethanol, for example. Ethanol will work, will dissolve more salicylic acid than the ester aspirin. So that's what we use crystallization is. Crystallization is used for improve the grade purity of a compound, correct? And take whatever the impurities, which is forming a mixture, take it away from the pure compound, correct? So that's what we use crystallization for. Again, it's the solubility is the key for the whole thing. So take that out. And if you remember, we talked about physical versus chemical properties, and just the keywords for physical and chemical properties is the two keywords. Any property is being observed. Any change is being carried out. That's the two keywords we have. Anytime I refer myself to a physical to a property, it means I'm observing this property. Anytime I'm looking at change, I am carrying out this change, correct? So what's the difference is between physical property or change or chemical property or change is that the sense chemical property and change observed or carried out under what? Changing composition. Changing composition. You start with pure substance or pure element, you'll end up with totally different compound or element, totally different. In the physical change or property, you start with the same material, the same composition of this material, you will end up what? The same material there, no change in the composition. What is changing only? The only thing changing is the state from liquid, solid, gas, or plasma, correct? That's what the difference between them. And I would like to look at the some of the, we went through this, but let's see if we can look at this. I think we looked at this before. And if you recall, just we went through this, and those examples here, those are inside iCollege. I post them for you there inside iCollege. And you can determine anytime, nothing changing, the composition is still there, everything intact. This will be physical. Anytime I change this, the material itself, therefore there will be physical. So as you see, a rusting bicycle, for example, here there is an example here. You look at this rusting bicycle, that's a chemical. See, chemical, you can see, because bicycle was running, everything is good, and then it was exposed to moisture and heat, and the iron of the made of this bicycle is being oxidized, rusted, oxidized, and therefore the whole thing is changing. So you end up having different material. Is the bicycle is transferred into different material. So, and frying an egg, and we talked about this. Frying an egg, that's a chemical, because you start with an egg with a protein. So depending on the temperature you're using, you might end up having different amino acids and different proteins you are producing, or different a mixture of amino acids and protein. And we talked, anytime I talk about physical properties like melting, boiling, freezing, all of those are physical, because you don't change. The states are changed, but the composition is not changing. whether you have an ice or a liquid H2O or ice H2O or vapor H2O. The composition does not change. 2 hydrogen atoms in ratio with 1 oxygen atom. Okay? So we talked about intensive versus extensive, and we saw it said IN means intensive. Anytime the pure substance is intensive, it means it does not depend its physical properties. The physical properties of this pure substance does not depend on the amount. For example, here's the density is an intensive. Why? Because I can measure the density of ethanol, say 10 moles of ethanol in the lab. I can determine the density of it, correct? But I can take trillion milliliters of ethanol. The density will come what? Will come the same, identical. It should not change, correct? This is what we call intensive property of the pure substance. The physical property does not change with the amount, but sometimes some physical properties do change. Volume, mass, temperature, those are very sensitive to the amount, correct? So if we have here no air conditioning and with the heat is going up, that will affect our status, will start sweating, correct? But will not start sweating if it's cooler, its temperature is cooled down, correct? So it's the amount is always changing the physical property, like such as volume, mass, temperature. But most of the physical properties we know, they are intensive. Boiling point, correct? Melting point, freezing point, those are the same. Boiling point, condensating point, they are the same. Deposition or this depositing point equal to the sublimation point, they are the same. So all those physical refractive index, density, correct? All those are intensive. It does not really depend on the amount, right? It does not depend on the amount. Those physical properties, they don't depend on the amount. You get the same thing. Now, we'll talk about the density, and then I'll show you how to look at the calculation. Density turns out to be a ratio. Ratio between what? Between a mass. Here, let me just go for between a mass between a mass and the volume. This ratio here very sensitive to what? First of all, temperature. You cannot give the value of a density without temperature, and then the pressure. So those are the two factors that are affecting the density itself. So those are two. Now in the lab, we'll have the opportunity to, I think in 2 weeks from now, not next week, we don't have lab, but after that we'll have measurements. Then after measurements in 2 weeks, I think we'll have, or 3 weeks, third week from now, we'll have the density. So we'll have the opportunity to look into this one and this one here. Dimensional method and displacement method. The mass will take direct the mass, will weigh an object. So we know the mass of this object, correct? Now, the only thing those two methods will differ based on the volume, how you measure the volume. You can take the volume here in dimensional method. You you'll be measuring volume. So you'll measure the volume here. Displacement method, you will take this object and immerse it in liquid such as H2O or ethanol, and see the difference of the displacement of this object by this liquid. That will be started with the initial amount of this liquid, whether it's H2O or ethanol. you immerse your object. This will elevate the liquid to a certain level, certain height. The difference between final and initial reading of the liquid, that will be the volume, correct? And as you will see, the displacement method will deliver for you with the assumption there's no air bubbles there, should give you very good data, the results. So the displacement, the dimensional method is dependent on the object, correct? If it's cube or square or this sphere. So all this dimensional method is very hard to determine the dimensional values of this object. So that's the error will come here. The error will come here. So therefore, the best one here is this one here. This is by far is the best. This is the best because you don't have the problem. But it has a problem. It has a catch here. We are assuming there is no air bubble. So we are assuming that whenever you insert your object, the object will displace the liquid from initial value to final value, and there is no interference by air. No air bubble is coming in. Sometimes there is air molecules inside, which is very, very minimum amount, which will not have a big effect, correct? But here, depending on this, here is always the problem here is shape. Oops. Here is the shape of the object will have a big issue because you have to measure it by vernier tool or by a ruler, but still there is an error because the shape of it will have a big effect. So, and here just an example here. Let me get out of this an example how to. Well, if you look at this is how we calculate the density. Now, in the past, ACS final exam does bring some of those, and even you will see your online OWL, it does have some of the density problems. So, because it's very important to calculate the density. So here it is. This is dimensional. Why is dimensional? Because it's measured the side. We have a cube. The cube is the height of the cube equal the length of the cube equal to the depth of the cube. So it has 3. So this is the height. This is the height here. This is the length. This is the height. And inside, this is your depth or width. Sometimes they call it width, or sometimes they call it depth. So that's a cube. So when you have those, then they are equal in the cube. So that's easy. So you just put them together and then you multiply those, and the volume is 27.0 centimeter cube. And make sure you understand that's in the lab as well. 1 ml is one ml here equal 1 centimeter cube. So 1 ml here, 1 ml always equal 1 centimeter cube. And some centimeter cube sometimes is called, somebody will go for nursing or for a physician training or physician program or assistant physician program. You'll hear the centimeter cube is written in the hospital as CC. the doctor will assign, tell the nurse, give this patient this time will boost up the amount. We'll give him, instead of 15 cc, give this patient 20 cc instead of 15. The patient needs help, so we'll give him more amount of the drug or of the medicine. So cc is called cubic centimeter. Cubic centimeter. So I can't write it here, but you can see this cubic centimeter, and that's used in the hospital. If you go to any your program related to any medicine or any health related program, you'll hear a lot of cc's relating on the drug or medicine you have. The doctor will give the instruction to the nurse. Correct. So cc means cubic centimeter, which is one cubic, 1 cc is 1 ml. Now we don't have sometimes a graduate cylinder that really measure 1 centimeter. So what we'll do in this, well, we have in this, we say, well, okay, here it is, 20 drops by the eyedropper is about, that's approximation, it's not exact, 1 ml or 1 cubic centimeter. So if we don't have the graduate cylinder or a pipette or a flask or automatic pirettes that can measure for us exact 1 milliliters, and we don't have the inside the experiment any exact quantitative data, we can take for, especially when you come to the experiment to that's 12 when you start identifying cations, anions, if you have iron 2 or iron 3 or zinc 2 ions, electrolytes. So then you have to use just 20 drops with the eyedropper or the pipette, 20 drops as about 1 milliliter or 1 centimeter cube. So any question you have? Yes. 20 drops, 20 drops, 20 drops, not milliliter, 20 drops. Take the eyedropper, correct? You take inside the eyedropper 20 drops. And then we go to your flask, and then you count the drops one by one. So 1, 2, 3, until you end 20, that would be roughly 1 milliliter. So if I say, well, do 3 milliliters, we don't have a graduate, for example, we are lacking for some reasons a graduate cylinder that measure for us 3 milliliters. So Dr. Ataya, can I take 60? Yes. 1 milliliter is 20 drops. So 3 milliliter will be what? 60 drops. It will be tedious to count 60, but at least we can get this lab over, correct? We will not wait to or cancel the lab or something like that. So this is always used for qualitative. We don't use it for quantitative, just qualitative, very crude. It's not exact though, but it comes, it turns out to be a very good estimation. It gives us a very good data. So it's not bad to know this. So now, if I look at this, this is the mass is given to you to be this, correct? The mass of this unknown metal cube is this, and the volume of it is this, correct? When you have these numbers together, the density will be gram per centimeter cube, gram per centimeter cube, correct? Gram per centimeter cube. So gram per centimeter cube. So if you look at this, this is gram per centimeter cube. Now, and that will give us then back to what we discussed Monday about remember the SIGFIX applications. We said we have to go through the SIGFIX application. Well, it turns out to be here. How many SIGFIX do we have here? How many? 6, okay. 6. And how many here? How many? 3. The least SIGFIX, because we have division, the rule will tell us if we have division and multiplication, the rule will go by the least sig figs number. So our answer has to have how many? 3. Our answer has to have 3 sig figs. And this is our answer here. Now, as you will see later on, that the units of the density will depend on the state of the object. In the solids here, let me go for it is. Change it so you don't sleep on me here. So let's change color here. Very good. So if I have a solid here, solids, then you will see the solids here. The unit is gram per centimeter cube, right? For solids. For liquids, then we don't have this. For liquids, we will have, let me take this one out. For liquids, we have gram per milliliter. Liquids, we have gram per milliliter. For gases, then we will have, those are the units, by the way. So those are units. So for gases, then, correct, we will have gram. You'll see the mass does not change. What's changing is the unit of the volume. And this one here, per liter. So gases can occupy they have no shape, but they occupy, their shape is the shape of the container they are in, and they are very spread out. So throughout the container itself or the room they are in. So solids are gram per centimeter cube, liquids gram per milliliter, and gases gram per liter. So you can get the idea of the units of the density. Now, saying this, I can get out of this one here. And let's see if we can find and share one of the density. Yeah, this is in your iCollege as well. You can see. And in the SS exam, you have to watch for the units. The key is the units. So you have to watch for the units. It has to come up to the correct sig figs. That's the key. So it's easy to calculate, and you have to look at the units. If it's tell you that's the given in gram, or sometimes tell you given, and it tells you give the density in kilogram, but it's given to you in grams. So you have to watch for this. So what I'm doing here it is. Just show you what's this worksheet. This worksheet is lacking one very important significant figure. So this is the mass, correct? So this one will be 12.9. Trying to get this one here, divided by 8. And that's not correct. Are you following me here, guys? That's not, the answer is not correct. Somebody will tell me why. This is so the idea is CHEM 0. 12.9, that's 3 sig figs, correct? And the 8 is 1 sig figs. So therefore, the answer here is not correct. Just to show you. The answer is what? No. The answer is 2, yeah, but the answer is 1 sig figs has to come to be. This is the least one, correct? So the least one here, I have this is, if this is 5 and above, we get change the color. If this is 5 and above, I round it up. So the answer is The answer is now is 2. 1 sig fix. So therefore, you'll see ACS exam will not give you something like this. Will give you 8 point something, 8.00, correct? For example. Are you following me here? Yes. Yes, will be 1.61. Okay, let's look at the second one. Let's take this one out. Let's take a second one. I have here 3 sig fix, correct? Same problem we have. We have the same problem here. So here it is. This is 3. However, this one, how much? How much? It's 1, not 2. Because I did not put a decimal here. If I put a decimal here somewhere, so if I put a decimal here somewhere, then it will. So let me just take this one out. And the pen is not working very well. So, but anyway, so if I put 50 and then the dot decimal, that will be 2. Then my answer will be 2, correct? But look here, he gave the answer, or the worksheet gave the answer, 0.87. Is this a correct answer? I took this one on purpose to show you that you understand when it comes to the final exam. So this is this a correct answer? No. This is not correct. So let me put this one here. Hold on. So what will be the answer then? 0.9. So the answer is 0.9. I'm trying to get this one here writing with me. So hold on. I'll answer your question, but gram per centimeter. Yes. Yes, if you are dealing with division and subtract, division and multiplication, that will be the least sig fix. The least sig fix. This is 1. This is 3 here. This is 1. So the least sig fix, because there is no decimal here. So you get the idea, guys? I'm gonna take the second one. The second one is correct. The answer. I'll take this one here. This one, how many? How many here? 2. How many here? It's 2. But this one is what? 3. Is this correct? No, that is not correct. That is what? That's not correct. So what's the answer will be? 38. Yes. What's that? For the first one? Number 2, that's 0.9, yeah. Yes, 1 sig fig. Yeah, this one here will be 0.9. Yeah, that's yes. 0.9, that's correct. Okay, guys. We'll go back and look at the sig fig rule here. Let's see here. Okay, guys, let me just take this one here out. Okay, so I gave you an example. That's in I college, and give you one without number. Consider this one first. We'll consider this. We'll consider this one here with first number. So, how many sig figs does this number have? How many sig figs? Well, it turns out to be, we'll ignore the 8 now, but just we're looking at this. Those are called decorating, correct? The first one. Those are called locating because there is no whole exact number before them. Exact number are always significant. Exact number are always significant, always significant. Those are trapped between whole 2 numbers, exact numbers 3 and 9. Those are okay, significant. Those are trapped between 4 and 5, significant. Those here has to meet 2 conditions. Last one, they have to meet 2 conditions. The first one, you have to have the decimal is present. which is here. And then they come after exact number, which is 1 in this case. Here it is. So those are significant. So for this, how many we have? Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. No, this is 16, not 19. We did not count the 8. Yeah, that's a 16. Now, if I put the 8 here, then those are now significant, correct? Because exact numbers coming in, and there is a decimal. Those are trapped between 4 and 8. All those are significant. And the sig fix will be how much? Will be 25. Will be 25. Are you following me here? The sig fix will be 25. So this is good. So now let's look at the sum of the worksheets. Just a reminder for us. Just quick here, you can just help me just solve this quick. The first one, how much? 3. The second one, 5. Number 3, 3. Number 4, 3, correct? Because the two conditions are met. The decimal is there and the exact number is there, correct? So this is 3. Look it out, I don't know why. So this is 3. This is 5. This is 3. This is 3. How much number 5? 1, correct. How about number 6? How much? 2, correct. We said the power, the exponent power has nothing to do with the what? So, and number 7, the 3 zeros are significant. They are trapped between 4 and 1, exact numbers. So they are significant. And the last one, 1.7, not allowing me to. So this is 2. I think that's more than enough. We'll come back and look at the significant figure application. So, and you can see number 11, maybe we'll do 11 and 12. Number 11, how much? 3. Okay. So this is pen is not very well. 3. Okay. And 12. 3. How about if I put here 5? How much is it? If I put 5, how much will be? I have how many zeros? 5, correct? Trapped between 6 and 5. And then this is 5 zeros. And then here 3, 8, and 5 would be how much? 9, correct. I think that's enough, and you can. How about 15? 1, correct. How about if I put the decimal here? All of them are count because the decimal is there, and the will be 5, correct? Good. That's good. We know how to do this. So now let's do take this one out. This is the answer for you. Just look at the answers. Those are inside the iCollege already. So let me look at the applications of the of significant figures. Here is the application of significant figure. If I'm dealing with the addition and subtraction, my answer has to be rounded off to the least digit, not sig fix, to the least digits after the decimal, correct? So, for example, I'm adding, let's do the addition here. I'm adding all those together. all those together here. Let me see. Adding this, and this. Correct? So how many digits we have here after the decimal? 2 digits after the decimal, correct? How many here? 1. How many here? 0. My answer has to have 0 digits after the decimal. So when I say 0 digits after the decimal, there is no decimal, correct? So my answer has to come up to a value that does not have a decimal. Everybody following? So when you add or subtract values and you want to round them to the correct answer, your answer has to be rounded off by the least number of digits after the decimal digits. Now, when I multiply or divide, then the least significant figure. So let's look at this. This is multiplication, correct? So how many is this one here? 4, correct? How many is here? 3. Which will win? The least number, which is half how many? 3. Correct? Which will be 3. So now, if I look at this, this is subtraction. So I have here how many? 2 digits, correct? And here how many? 1 digit. So I have to have 1 digit after the decimal. Are you following me here? So this is the rule here. So now I multiply all those together here. This is 2, correct? This is 2 here. This is 2. And this is 4. So the answer has to have the least digits, the least significant figure, because that's multiplication will be answered. Sig figs in 2 sig figs, correct? So, and the same thing here. Look at this. What you can expect your answer? Because here there is 0 digits, correct? That's a subtraction. And here 2 digits after the decimal, 2 digits. So my answer has to come 0 digits. So no decimal. No decimal. Correct? There will be no decimal there. So, and if I want to divide now, look at this. My division, I put the exponent by themselves. They have nothing to do with the sig figs determination. So I look at this. This is 4, and this is 5. My answer has to have 4 significant figures. Correct? Let me repeat now. The sig figs application rules will tell you if you are dealing with addition and subtraction, your answer has to be rounded off to the least. So you do your calculation with the calculator, you get the answer. Your answer has to come up with the least digits after the decimal. The least, when you are adding or subtracting, least digits after the decimal. Now, when you divide or multiply, then you are dealing with, your answer has to be rounded off after you get the whole number from the calculator as is. You round it off with the least significant figures. Correct, guys? So, okay, let me take this one out. And those just here tell you the sig figs and all the addition. So, yes. Yes, addition and subtraction. You look at the least digits after the decimal. Division, correct? Division and multiplication, you look at the sig figs, the least sig figs. There is the least digits, and the other one is the least sig figs. Least sig figs when you are dealing with the multiplication and division, correct? So, back there, please. So, okay, so let me take this animation out. And any question about this? So now, you know, when we come back to the density, you know, the density is, when we have this one here, 4, that's a division, correct? This is 6, correct? Let me just go and look at this one here. This is 6. This is 3. Your answer has to have the least one, the least significant figure. Not digits, that's division, correct? So, okay, guys. So, this one out. This is just an example, so you can look into them. Different pure substances, they have different densities, and densities are always given in most of the textbooks. 25 degrees, that's room temperature considered, and 1 atm, 1 atmospheric pressure, although the pressure is not written, but it's understood. This is the pressure is 1 atm at sea level, because when you go at higher elevation, the density might change because the volume will change. So the volume might change. So all, if you look at the H2O, for example, table, it depends on the temperature. So it depends on the temperature because the mass will not change. But if you heat, then the volume will expand. The density will drop a little bit. So those are just the material here. And I wanted to look at the examples here. Give you some examples. This problem, for example, give you the volume of 5 liquids, correct? And they have masses. And then you have to take each of this liquid has 25.00, correct, milliliter as volume. You divide each mass by the 25 and determine from the table here and the table here what compounds that might be. And the answer here is straightforward. It's just divide by the mass of each liquid by its volume here, and you get those values. So then you go to the table here, and you can determine the density here. So, and 0.708, that's diethyl ether. Diethyl ether is used for a long time, to get people into sleep. So, but no longer, it's not used now. So density for the second liquid is 0.7900. That's very hard because that will interfere with rubbing alcohol, will interfere with ethanol. That's very close density. So, but anyway, you can look at the example. Many liquids, you can look at those liquids, and then depending on the value, you can determine what liquids, what the unknown might be. Yes. No, you don't have to memorize. No, density values will be given to you in the exam. Yeah, but the main thing I want you to be aware of, that's the students might sometimes they don't forget. If I have one formula, I can make 2 formulas as one. So density here, I think the density is mass over the volume, correct? That's the main one. But the student, they don't realize that this one here, it has sub-formulas. And the ACS exam does not give you direct, give you just the sub-formulas. So I can say the mass here equal to density multiplied by volume. That's another formula. Or I can say volume equal to volume equal mass over density. So you have main formula, which is density mass over volume, and you have 2 sub-formulas out of the main sub-formula. And you have to be aware in chemistry when it comes to main formula, and then you can work it out. And then they ask you sometimes, they give you the density, they give you the volume, they ask you for the mass. Or the opposite, they give you the mass and the density. You have to work on the volume, correct? So you have to be aware that each main formula, you can make sub-formulas of the main formulas, correct? Here we have just one because it's 1 and 2. So we'll have 2 sub-formulas. If a formula has 3 or 4 variables, so we'll have 4 or 3 sub-formulas, depending on the variables here, mass and the volume. Here we have 2. independent variables, so we can make two subformulas out of this. So let me take this one out. Okay, physical change and chemical change, we talked about this. And just an example here, burning a candle. Those are just examples of the chemical change. Burning a candle, rusting of iron, baking a cake, electrolysis of H2O. And here just examples of a physical change. Light is given off, unexpected color change, bubbles are formed, different smell or taste, formation of a solid or liquid, whatever. So, and here's just some examples. If you look at the change here, correct? Look at the change, physical versus chemical. And this part here, you can see all this part here, all this part here, all this part here are chemical, correct? And all parts of this is physical. So if you mix, if you put an egg inside the pan, you have a car, not rusted. So, but you see, this is physical, this is chemical. Any question you have? Any question you have? Take this one out. Okay, so the last topic here in this chapter I would like to go through is the temperature. Temperature is very, very important aspect, which is here. We don't have the fourth, we have three, we'll use three, although. So we have three measurements. We have the metric. Let's take this one here. We have metric system, we have English system, we have international system, SI. So if you look at those three systems, those will take H2O as a reference. You will see H2O is used as a reference all over the places, correct? H2O is the reference for boiling point. H2O is the reference as melting point. H2O is the reference as fractive index. So you will see why we have selected H2O from all the liquids. Maybe there's a question here for you. Why the scientists are using a solvent H2O for many references. Now the boiling point is determined by a reference of H2O, boiling and freezing point of H2O. Somebody will tell me why? Well, the solvent you are selecting or choosing should have three characteristics. First of all, it comes in a pure state. H2O comes in very, very pure state. Second, it will pure state. Second, it is not poisonous. You cannot work in the lab with very poison hydrogen solvent to determine physical properties. That's a no-no, correct? So we use H2O it comes in a very pure state, very pure, very cheap, and non-poisonous, correct? So those are three characteristics of selecting a solvent as a reference. So if you book in chemistry or physics, most of the references are coming using H2O. Why? Because of these three. Cheap, comes very pure, you can distill it, you make out of very pure H2O. Cheap and non-poisonous, correct? And it comes in a very pure substance, three things. So now we are using, for the melting and freezing point, we are using the boiling point and freezing point, correct? Freezing point and the boiling point. If you look at those here, so if I'm dealing with the metric, H2O freezes at 0 degrees and boils at 100 centigrade Celsius, correct? So the difference is the scale of the metric scale is 100 degrees. That's the difference, correct? If I look at this, the English system, it has H2O freezes at 32. 32 is 0 centigrade Celsius, and boils at 212. So the difference between this is 180 degrees Fahrenheit, correct? Now, if you look at the international system, the H2O freezes at 273 and it boils at 373.15 Kelvin. So this is Kelvin here, correct? This is Fahrenheit. This is centigrade Celsius. Are you following me here? So now, out of this, you can come to the conclusion that 100 centigrade Celsius has to equal 180 Fahrenheit. 180 Fahrenheit has to equal what? 100 Kelvin. Out of this has to be 100 Kelvin. So those are 100 centigrade Celsius equal 180 equal 100 Kelvin. So I'll be using this for conversion. So for conversion, so I can use this one here for conversion. Here, this is very important relationship. I would say memorize it if you wish, but you don't have. But if you just look at the, so if I look at this one here, this is very important relationship. Yes. No, that's the scale, the difference between the boiling. We are going freezing to boiling. There's the difference between freezing and boiling. For all the three systems, you are using the same compound. For the same compound, you are using boiling and freezing scale. But they start, so centigrade Celsius here, 0. Then you have 32, that's the English. Then you have 273, your SI system. So then if you go further, then whenever you want to convert those here, you have to look at this. Just an example how to convert from centigrade Celsius to Fahrenheit Celsius and so on. So it's not really difficult. You can see here, you are looking for 15 degrees. It is, I'm looking 15 degrees. How much is in Fahrenheit? Well, you first get rid of the centigrade because the relationship is 180 Fahrenheit equal 100 centigrade Celsius. So the centigrade Celsius cancels 100. And then because you are 0 here, that's the metric. And the second one is all the way in the top, 32. So you can add the 32 to it, correct? That's because you are going from 15 centigrade to up. So you have to add up. If you go from Fahrenheit to metric, so you have to subtract the 32, correct? So this one will be 59. Now, let me show you something here. And you can see the examples here. Now, always you have to go through the metric easier. Now, sometimes you talk to yourself, I don't want to go through that. So from metric to English over centigrade Celsius. To Kelvin, you have to go first to the metric, easier. But there is a formula here I gave you here, which I discourage you from using it. If you want to get Kelvin, and then you have a Fahrenheit, you have to use this one here. But I will use this one here to centigrade Celsius, correct? And before you go, I'll just show you about something here, which is very important. Just hold on. Scientific calculator. Web. So there is I'm not downloading, it's not allowed, but here it is. This is a calculator here, guys. I recommend you to download it for free for your laptop. For your phone or iPad, you have to download it. You have to pay for it. Now, why is this recommended for the conversion? Look at this. It has a sidebar at the end. I'll click on the sidebar here. All the conversion you can imagine, they are there. So if I look at the temperature, click on temperature, then I say, okay, how about if I have 55 centigrade Celsius? Okay, the 55 centigrade Celsius is given to me equal to 131 Fahrenheit, equal to, this is the English system, equal to 328.15 Kelvin. So if you want me, I can put an announcement how to download this one for free in laptop and desktop, but not for iPhone, for your phones, not the phone. Your phone you have to pay $25, I think. I'm not associating myself with this Texas electrical engineering. Through the years, I'm using it over 15 years now. It's a very good calculator. I'll talk to you then.